There we go. Now I'm unmuted. All right, so former classes had got an exam this Wednesday, Thursday. You guys all ready for it? Fantastic. All right, busy time. All right, let's go ahead and keep on keeping on in chapter 22. So the other day, we just sort of started to talk about reactions of acid chlorides. So I think I did the first one, right? I showed you how an acid chloride can react with a carboxylate, right? Just a negatively charged, basically a deprotonated carboxylic acid. About as straightforward of a mechanism as you can possibly have. It just comes in, replaces your Cl, boom, you have an anhydride. For the most part, the rest of the acid chloride reactions maybe not quite that simple, but they're close. They're very, very straightforward since Cl minus is such a good leading group. All right. So keep it on with reactions of acid chlorides. I mentioned the other day that basically the purpose of reactions of all these compounds, the major purpose is going to be to make other carboxylic acid derivatives. Right? We saw that with acid chlorides forming anhydrides. We can also see it with the other ones as well. All right. Here's one common setup that you'll see is that you can react acid chlorides with water. And you also add a little pyridine to sort of help it along. Just as a reminder, that is pyridine, right? We've used it before here and there. We use it as a weak base. So when the time comes to actually use this as in the mechanism, we're going to be using it as a weak base. You don't necessarily have to have this there to get the reaction to proceed, but it sort of helps it along, helps it to complete a little bit faster. Right? One thing that's kind of cool and kind of creepy at the same time is this reaction, like I said, will happen on its own without pyridine. If I could have brought down a bottle of an acid chloride. One thing that you can do with it, you can just open it, let it sit there open for a minute or so, and just sort of watch it. If you watch that acid chloride, or the area above the acid chloride bottle, you'll actually see this white smoke start to appear. There's actually a picture of it in your book. I elected not to do it here because I didn't want the people on the front row sniffing up hydrochloric acid fumes. You're welcome. Because basically that's what happens there. The acid chloride is reacting with the water in the air, just the humidity, to make its product. And HCl is actually one of the byproducts. So it's pretty nasty stuff, but it's also kind of neat to look at. All right. Let's see how this is going to go. Well, as always, I want to get your opinion. All right, any ideas on what the first step of that mechanism could be? You got an acid chloride, it's got an exceptionally good leaving group, you got water, you got pyridine. But what's been the usual modus operandi for these types of compounds? What usually happens to that carbonyl group? Yeah, carbonyl carbon likes to get attacked, right? It's a good subject for nucleophilic attack. That Cl is going to be a really good leaving group. So now the question is, what attacks it? Well, you really only got two choices, right? It's the water and the pyridine. Which one do you think it is? It's water, yeah. Got electrons on oxygen here. It's a very weak nucleophile, but since Cl is such a good leaving group, It's good enough of a nucleophile. And that leaves you with that. All right, now what do you think is going to happen? Close. It's not going to be CO. What else can act as a base to grab an H? Pyridine. Yeah, this is why we have the pyridine in here, because it is a weak base. I'm just going to draw pyridine because I don't want to draw that structure over and over again. Since it's weakly basic, it can come in and grab that pretty quickly. Like I said, this would happen without the pyridine, but pyridine makes it a little bit more efficient. And you see, the primary organic product here is that. That is a carboxylic acid. So that's one of the ways that you can make a carboxylic acid, is take an acid chloride, react it with water in the presence of pyridine. Okay. Does that make sense? Questions? Here's a question for you. You've seen how we make carboxylic acids from acid chlorides. Do you think we can make an ester? Well, of course you can. I wouldn't be asking you otherwise. Better question, how do you think we could make an ester from an acid chloride? Think about that. What is an ester? What's the key feature of an ester functional group? What does an ester look like? Yeah. Yeah, that's what an ester looks like. So, just hypothesize to yourself and then share it. How do you think we might be able to make an ester from an acid chloride? Just based on what you know. Well, what's the only difference between an ester and an acid? It's that extra R group, right? So basically you're trying to figure out, okay, how can I get that same basic structure except have the H gone and replaced with the R group? Would you want to use water as your primary reactant? No. What do you think you might want to use instead? An alcohol, boom. Yeah. Let's see what happens with an alcohol. Okay, so let's see. I'll use this guy. I'll use isopropyl alcohol. All right, you can have basically the same setup there, right? Still going to have pyridine act as a weak base, but the only thing we're going to change is we're going to replace the water with an alcohol. And this can be, any alcohol. Just depends on what your R group you want to be there, right? Remember what I've told you in the past about alcohols. Their reactivities and their tendencies are very similar to water. Well, what did we just see water do in the last reaction? Attack the carbonyl carbon. Hey, guess what? An alcohol group can do that too. And what it gives you after attack is a protonated ester. Last time, in the last example, we took pyridine. We used that as the base to kind of try to deprotonate the final product. It's going to do the exact same thing here, right? So this is kind of nice because the mechanism of this process is exactly the same as you previously learned. The only difference is your nucleophile is an alcohol and not water. And that's how you end up with an ester. So this is kind of like a reaction pair here. They basically are the same, just different nucleophiles. Okay. So far, so good? Any questions? All right. Got another question for you as soon as I erase this. Again, based off of what we've been talking about, how do you think we might get a primary amide? What's a primary amide? That's a primary amide. How do you think we might get a primary amide from an acid chloride? Well, just ask yourself the question, what am I trying to get onto the carbonyl carbon? It's an NH2, right? So what do you think you're going to add? What's that, Marissa? NH3, ammonia. That seems like a reasonable guess. Let's try it out. Okay, that's ammonia, NH3. Ammonia is a weak base and also a weak nucleophile, but it's actually stronger than water and alcohols. So if water can act as a nucleophile in this case, certainly ammonia can. Yeah, it's even a better nucleophile than water is in this case. So lather, rinse, repeat, right? Nucleophile attacks your carbonyl, Cl minus leaves. You end up with this. Now, there is one difference between this type of reaction and the last two. All right, in the last two, we use pyridine, right, as a weak base to protonate. We actually don't have to add any pyridine here. We just have to make sure that we add 2 equivalents of NH3 because we just said NH3 itself is a weak base, right? It's just as good as pyridine. So in this case, another ammonia can come along, deprotonate that. And that gives you your primary amide. And the ammonium ion as well. Okay. So far, so good. Any questions? You're saying, hey, yeah, these really aren't that bad. No, they're not. How could you make a secondary amide? What's the difference between a primary and a secondary amide? The N has, instead of the N having two H's, it's got one H and one R. So what do you think you would use as the nucleophile in this case? Let's say my target was this. If that was my target, what do you think my nucleophile is going to be? Well, you pontificate that. I'm going to Google something real quick. Yeah, it is. Yeah, just a two-carbon amine. A primary amine, all right? Remember this. So if you want to make a primary amide from an acid chloride, use ammonia. If you want to make a secondary amide, use a primary amine. Mechanism works exactly the same way as the last one did. The only difference is the presence of that R group. Okay? That's a tertiary amide. Right? Going off the logic of what we've been doing, what do you think we're going to need to make a tertiary amide? Make a primary amide, we needed ammonia. To make a secondary amide, we needed a primary amine. Secondary amine, yeah. Again, works exactly the same way as the other mechanisms. So reactions of acid chlorides are highly varied in the terms of what they can make. But in terms of mechanisms, they're very, very vanilla, right? There's not a whole lot of variation in between. This method, in fact, is how one of the most, probably, for you guys, probably one of the most widely used chemical agents is made. You guys ever use DEET? You guys know what DEET is? What's DEET found in? Bug repellent, yeah. DEET is an acronym. It stands for, the full name of it, of the compound is N,N-diethylmetatoluamide. It looks like this. This is DEET. Commercially, DEET is made from this acid chloride, using the same basic reactions that we've been doing. So there you go. There's a pretty neat little real-world application of this. I love DEET because mosquitoes are attracted to be something awful outside, so DEET is a lifesaver. All right. Cool, cool. Any questions about reactions of acid chlorides? So you're still writing. I'll stall for a second, give you time to finish, blah, blah, blah. Can I erase? Once, twice, okay. All right. Let's take a look at reactions of anhydrides. Okay. All right, now remember, first of all, there's a couple of different types of anhydrides. There's symmetrical and mixed. And that can make a difference on what exactly you get in certain circumstances. The first one here is very, very simple. Let's say you have, we'll use a symmetrical anhydride. All right, first of all, simply, you can just react it directly with water. Nothing else needed, not even purity, just water. All right? Well, what do you think water's going to do? If you don't know by now, then maybe just not been paying attention. What's water going to do? It's going to, yeah, exactly. It's going to attack a carbonyl carbon. Which one? Doesn't matter. It's symmetrical, right? They're both the same. So we'll just pick one. All right. It's going to attack there. The difference here is instead of the leaving group being Cl minus, the leaving group is going to be a carboxylate ion. So that whole thing right there is going to be your leaving group. And here's why we don't need pyridine to act as a weak base. All right? So we're going to end up with a protonated carboxylic acid. And our leaving group is still there, our carboxylate ion. What do you think is going to happen here? What's that?
The leaving group is going to go to hydrogen.
It's going to lose a hydrogen to where? Yeah. There's a very easy way to make both of these species neutral, and that's a proton transfer from one to the other. So we end up with two equivalents of that carboxylic acid. And that's what you always end up with when you react a symmetrical anhydride with water. Symmetrical anhydride plus water gives you two equivalents of the same carboxylic acid. Okay? Does that make sense? So far, so good? Can I erase? All right. Let's try it with a mixed anhydride. Like that. Okay. Now going from a symmetrical to a mixed anhydride, it makes no difference in the mechanism. The mechanism is still the same. However, you may think in looking at this, okay, well, we got water. Now our carbonyl groups are not the same, right? So which one's it going to attack? Or will it attack both of them? Ultimately, you're right, Eli, it doesn't matter. In reality, what happens is this will attack both of them. It's not going to have a preference, all right? However, you're going to see in the end it actually doesn't matter, all right? Let's just say, hypothetically, that it attacks that. That leaving group leaves. Excuse me. So you end up with a carboxylate and a protonated acid. And just like last time, we'll get a proton transfer. All right. The big difference between using a mixed anhydride and a symmetrical anhydride. Symmetrical gave you two equivalents of an identical acid. In this case, you're going to get two different acids, which makes sense, right? The two sides are non-equivalent, so they should give you non-equivalent acids. You still get two acids, they're just different. Does that make sense? Here's a question. What would I have gotten if instead of attacking here, I attacked here? You would have gotten the exact same thing, right? So in this case, it actually doesn't matter which one you draw it to. You get the same. So in a nutshell, when you're looking at this, it's pretty easy. You just sort of divide these up right over here, put an OH at the end of each one, you've got your products. That make sense? Questions? All right. All right, so we're not using water here. We're going to use 1-propanol. Any predictions on what type of final products this is going to make? An alcohol and an ester? I don't know. Let's see. All right. Remember, water behaves basically the same as alcohols, right? So, since water was a nucleophile, this can be too. So what I'm going to do is mixed anhydride. Again, doesn't matter which one gets attacked. Excuse me, sorry, not mixed. Symmetrical anhydride, doesn't matter which carbonyl gets attacked, they're the same. Carboxy group leaves. There's your carboxylate. There's your other species. And just like we've seen previously, the protonated species can donate a proton to your unprotonated species, right? Same exact process, just using an alcohol as your nucleophile. However, this does make a bit of a difference with the products, right? With previous results, we've seen that we got two acids. Now we get one carboxylic acid and one ester. So that's always what you end up with whenever you react an anhydride with an alcohol. Half ester, half acids in the product. Okay? That make sense? Any questions so far? All right, here's where things get a little bit hairy. Let's try a mixed anhydride. Stick an extra carbon there. Let's use this. All right, this is where things get a little bit different, a little bit more complicated, right? Now, in the last example, we saw that when you had a mixed anhydride and you reacted it with water, did it matter where the water attacked? No, because we ended up with the same thing anyway. You always ended up with a carboxylate and a protonated acid. Proton transfer, you always ended up with two acids. Here, though, I think you're going to see it's probably going to make a difference, right? Let's just say that this guy reacted over here. And that guy left, all right? I'm going to fast forward through the mechanism. I think you guys have been through the mechanism enough now to kind of predict how it's going to go, right? So the carboxylate is eventually going to form your carboxylic acid. And this combines with this to make your ester. All right, running out of space there a little bit. I can go through the mechanism if you need me to, but I don't really think it's necessary. Do y'all see where I got those products from? All right. Now I'm going to redraw this down here, though. To show you that we get something different if we attack here and this leaves. Right? If this is the case, then this is your carboxylate. And you notice your carboxylate here has one extra carbon than the one here does. And you know your carboxylate eventually becomes your carboxylic acid. This combines with this to make your ester. All right, as you look from the top line to the bottom line, are these two the same? No. Are these two the same? No. So guess what? You get all of them. Because there's nothing really that favors attack of one of those carbonyl groups over the other. All right, so if you have a mixed anhydride plus an alcohol, you're going to get 4 different products. 2 carboxylic acids and 2 esters. So this is kind of the first one I think that we've run into that's a little bit more complicated than some of the other ones. Right, you just have to count. The mechanism's not complicated, but there's just multiple places it can occur. Okay. Does that make sense? Any questions so far? All right. You think we can react anhydrides with anything else? Well, of course we can, not even looking at your responses. Of course we can. Question is what? What else might we try reacting an anhydride with? What's that? I thought I heard something, but mask muffle. That and the voices in my head. That's not a joke. Heck, let's try it with ammonia and see what happens. Right. symmetrical anhydride, and ammonia. I'd love to tell you there's some surprises here, but there's not. Works the same old way the other ones have been. Nucleophile attacks a carbonyl carbon, doesn't matter which one. One second. There is one little twist to this. I just want to make sure I remember it right before I draw it. All right. All right. Yeah. So this one does have a little twist at the end here. What would we expect to happen based off of previous results? Proton transfer, right? This is not the product, so by the way, I'm just drawing this to show you something. We would expect to get a proton transfer and see this. But remember, this is an acid, right? This is still weakly basic. So because this is an acid, this is a base, they don't want to exist in this state. This wants to give up a proton slightly. This wants to accept a proton slightly. So you'd end up with that. So that actually doesn't happen here. Here's what we have to do here to get our target. We actually do need to add 2 equivalents of ammonia. All right. We put the ammonia, extra ammonia in because ammonia by itself is more basic than an amide. So this will deprotonate that, and that gives us our real target product here. We're trying to make a primary amide. You also end up with this. That's an ammonium carboxylate salt. Just like an NaCl, for example. It's a salt. So we don't end up with a carboxylic acid here. This is waste product. This really is not very useful. Your real target here is to make that primary. Okay? So, anhydride, 2 equivalents of ammonia gives you primary amide. How do you think we make a secondary amide? Use a primary amine. How do you think we make a tertiary amide? Secondary amine, just like we saw with acid chlorides. Okay, so that's not any different. All right, mixed anhydride. How do you think this changes things? Or will it? If you look closely at this, you're going to get 2 different amide products, right? Because just like we saw with alcohols, you can attack either one of those carbonyls. We'll just do that one for fun. Okay. So whichever carbon gets attacked, that is the basis for your amide. So fast forwarding through the mechanism, attack at that carbon is going to give you that primary amide. And give you this ammonium salt. Okay. Now it's important to realize, though, that's not the only place you can get attacked. Right? You could have, of course, you could have attacked that one instead. And if you draw out the product there, you see that this amide product is different than that one. So yeah, you're going to get two different amide products as a result of this. And just like we saw before, if we wanted secondary amides, we'd use primary amines. If we wanted tertiary amides, we'd use secondary amines. Okay. So bottom line, when reacting anhydrides, the easiest one to deal with is reacting with water because it's very, very predictable. Can get a little bit more complicated if you have mixed anhydrides with either amines or alcohols. Yeah. How are we doing so far? Any questions? Sounding good? Waiting out the clock. Thank you for not nodding directly when I said that. Yeah. Keeps the hurt on the inside. All right. All right, that wraps it up for reactions of anhydrides. You may probably have guessed by now that you're kind of in like a gauntlet of reactions here. There's a ton of them in this chapter. One nice thing, though, about acid chlorides and anhydrides is that they're fairly predictable, right? There's not a whole lot of variety. Now we're going to get to reactions with carboxylic acids. And this is where things get a little bit different. Most notably because if you look at a carboxylic acid, what's your leaving group? What's your theoretical leaving group here if something just directly attached itself to the carbonyl carbon? What would have to leave? I think I heard somebody whisper it, but I'm not sure. What's that? Yeah, OH minus would have to be your leaving group. How does OH minus rate as a leaving group, good or bad? It's a strong base, so what type of leaving group is it? Uh-oh. Think way back to chapter 7. What makes good leaving groups? Weak bases or strong bases? You are correct, sir. They are not good leaving groups. They're terrible leaving groups, in fact. That's going to complicate things. So we can't necessarily just send in a nucleophile to attack that carbonyl carbon and replace it, right? We got to get a little bit creative, right? So, however, there are a few things you can do with acids despite this. You just, like I said, have to work around the limitations. Here's the first one. Let's say we have an acid, right? One thing that we can react it with is a compound called thionyl chloride. Thionyl chloride is SOCl2. We've seen it before. We haven't used it that much, but we used it once in the last semester. All right. Okay, so if we look at this, this one's going to start off a little bit different. In this case, what's actually going to happen is your nucleophile is going to be this oxygen. Your nucleophile doesn't come from here. This is your nucleophile. That OH is going to attack something. What do you think it's going to attack? You got a partially negative oxygen. What do you think it's going to attack? You see anything with a positive or partial positive in your other structure? Out of the S, the O, and the Cl, which one do you think is the least electronegative? Sulfur. Yeah. This has got a nice, strong partial positive. This is basically like a carbonyl carbon there. Right? So this oxygen is going to attack that sulfur, and when it does, it's going to knock off one of your Cl minuses. So now you have an oxygen-sulfur bond. You got a positive charge. That Cl minus that you just knocked off can come back. It can grab an H from that oxygen. Give you this. So basically what we've done here is we've transformed our OH, which was a terrible, terrible leaving group, into something else. This is a good leaving group. So now we can actually have attack on your carbonyl carbon. That HCl that you just made here will dissociate in the solvent, give you H plus Cl minus. So you're still going to have Cl minus floating around in there. That Cl minus, by the way, Cl minus is a terrible nucleophile. It's really, really weak. But it's strong enough to knock this off. That's how good of a leaving group it is. So that's going to attack there. This bond's going to break, and actually you get a little bit of a rearrangement in your byproducts. Not really that important for you guys, but I want to show it to you correctly. And Viola, you see, you end up making an acid chloride. And then you get SO2 and Cl minus as byproducts. And this is really important. How many other ways do you know to make an acid chloride? None, because this is the first one you've learned. This will be the only way you learn to make an acid chloride. If you need to make an acid chloride, that's it, right? Have an acid, you have thionyl chloride. So if you need to go through an acid chloride in a synthesis problem, that's going to be a pretty important reaction to know. Okay? Definitely didn't go by traditional means, at least the ones we've learned so far, but still gets us there. All right. Any questions on this? All right, we're about out of time. Be studying for your test. If you have any questions along the way, please feel free to let me know. I'm always here, through email, in person, whatever. In case you're not aware, or I didn't make it clear enough, this stuff is not on this next test. So chapter 22 is not on the test. It's just 18, 20, and 21. Okay. All right. Have a good one. Yes. I'm sorry? We can if you would like. Would you like to have a Q&A review on Wednesday? We can do that. All right, plan Q&A review Wednesday morning.